A few days ago, I got a comment on one of my YouTube videos asking me how much skill, like natural born talent that you have, helps you get to a PhD program versus how much of it is just hard work and doing homework problems and stuff like that. Like, how much do you attribute to natural born talent versus honing a skill? And I wanted to go in a little bit more depth about my personal upbringing and my skills in math, and how much of it started out as just natural born talent and when that transitioned over to insane amounts of practice. So I've divided it up into 5 categories: the K-12 years, the first 2 years of college, the last 2 years of college, which really that should say 5 because it took me 5 years to graduate college, sadly. And then we have the master's program and then my PhD program. So we'll start with K-12. Growing up, my dad was pretty involved in my schoolwork. I always had him helping me with stuff that I struggled with in school and helping me understand certain concepts if the topics were too tough. Because my dad was at one point a middle school science teacher, science and math. So, but by the time I was in school, he no longer did that. But he still had that teacher mentality. So it was kind of like wherever my teachers at school fell short, he was able to fill in the details. So I had that helping me, and I also had the fact that, I was kind of interested in science in general. It wasn't necessarily math, but I had an interest in, the planets. I really wanted to be an astronaut when I was very little, and I would read encyclopedias about that type of stuff. And I was also interested in dinosaurs, not so much earth science. I was really interested in chemistry too. But I wouldn't really say I was that interested in math, but I did love the sciences, and when I was in really young elementary school, I think that also contributed to it. So that was my own personal interest helping me. And then by the 8th grade, that's when I started doing algebra, like college algebra, and then in high school, we started doing interesting math, I'll call it. So I think 8th grade was when I really got interested in math, and I was always wanting to do the next hardest thing. I remember a lot of people struggling with Algebra 1, but I liked it. I thought that the problems were interesting, and I remember solving the quadratic formula for the first time in 8th grade towards the end, and I found that very satisfying, how that formula was derived. So the fact that I was very interested in it, and I did have it was mostly natural born talent. I think my brain was just built for that type of stuff in high school. So I had a reputation for being really good at math and science. English, not so much. I was not good at reading and writing, unfortunately, because I didn't like reading nonfiction. Well, I liked reading nonfiction. Like if I was going to read a book about the state of Utah, then that was way more interesting to me than reading a book like Harry Potter or something. I don't know. So in high school, I kind of breezed through everything. Trigonometry was nothing. I put in a little bit of effort for trig, but if I got too lazy, I'd fall behind. But for trig, it was easy. Calculus 1, they don't even do I think they briefly touch on the antiderivative in senior year of high school if you take their calculus course. But at that point, I was taking college courses, and they go in farther depth with calculus. So for K-12, I would say that natural born talent kind of saved me, and it gave me a false sense of security of how good at math I was. And the first 2 years of college didn't really help either, because during those 2 years, I took calculus 1, 2, and 3, and those classes were simple to understand, but they needed practice. But I had so much interest in calculus, and I felt like I was doing something amazing by being able to solve those calc problems in the Stewart book, that I would just stay up late at night and practice. I would do all the homework problems, and I would look else and see what's in there and see if I could try it. I remember I tried doing an application problem with Newton's law of cooling, I believe it was. Like, how long can I leave a can of pop in the freezer before it, bursts? I think I remember doing that by myself. So I loved it, and also I took differential equations here. I remember differential equations and calculus 3 being tedious, but not hard. Like, it was really easy to make a mistake and get the wrong answer. So I was annoyed with those classes because I understood the concepts, like what was going on and how to solve problems. But it would take me like an hour to make sure that I didn't screw it up. But I did both of those classes, and I took math proofs and elementary linear algebra. I did those 2 classes as independent studies. I think if I took elementary linear algebra as, a normal class, then I wouldn't have struggled with it, but I was not good at independent studying. I relied too much on the teacher to tell me and explain me things. I couldn't read math books because I didn't like reading, and the same was true for math books. But for math proofs, the instructor gave me a lot more attention that he should have. He was a hand holder, which I was very thankful for, but it's good in the moment, but you pay for it later. And when I took the class, I ended up getting an A in it, but it did not prepare me for university level math, because that was years 3 and 5 when, that was proof-based mathematics. That's where real variables rears its ugly head, and abstract algebra is in there too. So I would say K-12's natural born talent, years 1 and 2, again, natural born talent, but also just an enthusiasm for the subject because I would do it voluntarily. But then when I got to university during these years, the proof-based mathematics just absolutely wrecked me. Computation was no big deal. Like, if there was no proofs involved, then I didn't have any problem with it. But the proofs, just like proving De Morgan's law, I remember that was a homework problem we had once. And I remember doing it, but it was just, I didn't have any good feel for it. And because I didn't have a good understanding of proofs, I thought that if this was what mathematics was like at the end of your university degree, then it wasn't for me. I also had some bad teachers in there, unfortunately, during these years. So that's why I left mathematics. I thought it was too hard for me, and I got my degree in environmental science. But I had friends that stayed in the program, and I kind of was jealous. This is kind of not a good reason to do a degree. But because of, how much I loved math during these years, and how much I walked away from it during these years, and I had friends that finished it, it made me really want to go back and get a degree in mathematics, because it felt like the thing I should be doing. I do what I think I should do. Well, okay. I was going to say I do the things I think I should do, not the things I want to do, but that's absolutely not true. I'll play video games one night if I really don't want to do my Fourier analysis homework. So I got to keep myself honest. But during the master's program, I applied to a couple math programs, but also some environmental science programs. And I got accepted into a math master's, and my friend was going to go into that program as well. So that's part of the reason why I did it, because I really wanted to get back into mathematics. So I entered the master's program. They made me take real variables and abstract algebra at the undergrad level because I didn't have these years in math. So that was my first year. And my second year is when I took measure theory and abstract algebra instead of modern algebra, which is just the graduate level version. And I remember at first it took me a while to get used to it, but I had to look up a lot of stuff on the internet to get comfortable. The books that we had were good. I will say that. The books that we had during these years was good, except for maybe the Zygmunt Whedon book. I know I use that book a lot these days. It's hard to look up information in that book. But to comment on how much my talents were helping me here, it was very little. I had to look up a lot of solutions on the internet, And I felt guilty about doing that because it just feels like I'm just copying what other people are doing. But I had to reason with myself, like, look, I'll borrow the information now, but I'll get comfortable with it later. I think my probability theory instructor also said something like that when I took his class during these years, because he says, well, as long as you do it not knowing how, by just watching me, but then it becomes yours. No one starts out running marathons. You have to crawl first. So there's like a transition. The math proofs is the big barrier. And I ended up taking I take math proofs like 4 times, because what I did was I took the independent study. I got to university, couldn't do real variables, so I dropped it, and I signed up for their math proofs program. So that was my second attempt. And then my third attempt was when I took a computer science course, which was called Discrete Structures. And I really didn't need to take it because it was kind of low level. It's math proofs for computer scientists. So that was the third time I took it. And because I did well in it, because it was my third time, the instructor asked me if I would be a teaching assistant for the class, and I said yes. So the teaching assistant position was the 4th time I took math proofs, because then at that point I was telling other people how to prove stuff. And it was because of that I became a lot more comfortable. That's where practice picks up with doing what was I saying? I just distracted myself. That's where practice overtakes natural born talent. And because of that, it helped me succeed in the master's program, because I could do a lot of problems by myself, but there were more problems that I just had to look up, because it's like, where would you come up with this trick? Sometimes I'll see that, like, where would this come up? I was also not doing myself any favors by not reading the textbooks. This was the big issue. I would just use class notes and sometimes look stuff up in the book if I needed them. What I was not doing is what I ended up doing in the PhD program. So let me move on to here. The first year of the PhD program, I took abstract algebra, real analysis, and complex analysis. And I did not take very good notes, but I was more comfortable reading books. And it was because I took bad notes and because I knew that how tough that qual was going to be, I was like, oh crap, I really do need to study harder, because this stuff is not intuitive to me at all. I'm really struggling here. I thought master's was hard, but PhD was like they're going another step. And that's when I started reading like a madman. I just started reading not all these books you see, but a lot of these books you see, I started reading and taking notes over. You've seen my other YouTube videos. And so in the PhD program, I would say natural born talent plays almost no role. It plays some role, but it plays a role for everyone, because every single person that's in the PhD program, at their high school, they were probably the top math student in their high school. Probably, maybe not everyone, but when you see what kind of math that they're doing at PhD, like the homework problems they can do and the papers that they read and how many books they read, they're comparable to me. So when I saw, maybe that first year that I wasn't doing as much as I should have been doing, and I was also afraid of that test, that's when it became all practice. And eventually, all those years of practice, they add up, and then you just see the solution to a lot of these measure theory problems. Like over the Christmas break, I took this book with me. I took this book home with me, and I opened it up to like chapter 3, because I was interested in seeing like how obvious, because when I was in the master's program and I had this book, I looked at these problems, I was like, ugh, oh my gosh, I can't do any of these problems. But then I was looking at these, problems over the break, and I read through it, and I was like, oh, that doesn't really seem as bad as I thought it would. You start to see things after years of practice. Like number 10, for example. Look how simple 10 is. Show that the measure of the union plus the measure of the intersection is equal to the sum of measures. I remember a problem like that would have given me a headache, because it's an easy statement, right? Even when I was a master's, like, okay, that's an easy statement, but how do you prove it? That was back when I didn't have as much skill as I have now. But after 5 years, maybe even 6 years now, of just reading all these measure theory books, I look at that and go like, oh, I know what to do. So eventually practice becomes talent. It's not natural born talent, but you do get better, and you see yourself get better. So, and it helps you. It helps you because you need that when you're trying to work on research problems, which is kind of what I want to do now. So let me talk about this result that we did in my geometry course. So this is a known result. I'm not sure which books you see it in. I think it's called Alexandrov's theorem. I'm not sure. But here's what the theorem says. You have an origin symmetric convex body K in Rn. And it says that for any unit vector in the direction of the sphere, so this is the n-1 sphere. It's just, think of the unit sphere in Rn, but you're missing the inside of it. You're just looking at the shell. So xi is just a direction of length 1. Whichever direction you pick. Then the n-1 volume of your body K intersected with the plane that's orthogonal to that vector. So this volume, this n-1 volume, which think of it as area, if n is equal to 3, then this is just the Euclidean ball in R3 with hollow inside. And then the area of the cross-section that you slice, if K is a potato, you just slice the potato in any way. If the area of the potato chip that you create is absolutely constant, meaning that it's independent of your, I guess it'd be your direction xi. Well, okay, it has to be constant regardless of how you cut it. So your area is always constant. Then the conclusion is that K must be some ball, meaning it's your body K is the ball. Because balls, no matter where you slice them through the center, they're always that circle. You know what I mean? So the area of that circle is always constant regardless of how you cut K. So this is a theorem. It tells you something about a body K if you know something about the area of the cross-sections. And here is the proof of it. Now, I am cheating a little bit here because this proof uses another result, a lemma if you want, and I don't have the proof of the lemma. So we talked about it at a later date. So he gave us, the fruits and vegetables, as he says it, and then he had to explain where the lemma comes from. But here's how it's proved. So we use this function called rho k. Rho k is called the radial function. And the radial function is defined as the maximum of lambda, such that lambda times your angle theta is an element of k. So theta is a direction that you have in your cross-section. And you pick, so if I were to draw a picture, it's easier to explain with a picture. So let's say that this is your cross-section. And here is the center. You pick a direction, let's say it's theta. So this is my vector theta. And the radial function says, okay, it's the lambda that takes you until you hit the boundary. So the length of this vector that you have to multiply by theta, lambda theta, that length is what the radial function is. Now, we look at the area of the cross-sections. Think of the three-dimensional case because it's just easier that way. So the n-1 volume of K intersected with your plane, which is just the area of the potato chip, is by definition equal to the integral over that subspace that you have, the orthogonal subspace, of the characteristic function of Kp dp, and where this is the differential of the two-dimensional Lebesgue measure. It just returns the area of the shape. That's all it does, the cross-section. And then you pass through polar coordinates. So by polar coordinates, we're looking at the radius and this d sigma, which represents the, it's essentially equivalent to, hold on, let me make sure I don't screw this up. It's basically the measure instead of area. Like in the coordinate space, you have area like this, but in polar coordinates, you have more of like, you're measuring how much area you get when you rotate. I'm not explaining that very well, but it's just polar coordinates. That's all it is. You're passing through polar coordinates when you go from here to here. So you get this characteristic function times of the radius times sigma, and then this is your Jacobian that sits out here when you do a change of variables. And when you integrate from 0 to infinity, you really only go up to the value of your radial function, because once you get outside of k, you just get 0. So it doesn't make any sense just to go up to. It only makes sense when you go up to rho k. So one way that we can write this is, I've explained it kind of here, I wrote kind of sloppy here, but the integral of x times the characteristic function of e is just the integral of f over e. That's all that I do here. So I can move this guy so to speak, up here by just writing rho k sigma. And then it just becomes an integral that you can evaluate. So just add 1 to the exponent, divide by the new exponent. When you add to the exponent 1, you'll get n minus 1, which is where this comes from. If you plug in 0, you get nothing. If you plug in this, you get this. And then you have to divide by n minus 1 by pulling it out here. And then you just get this singular integral. So this is what we have. This is what the two-dimensional, or not two-dimensional, but the n minus 1 volume of the cross-section is. Okay, so notice that when you integrate over the sphere intersected with the orthogonal subspace, that's your chip that you want to use your radial function on. So this is the chip. This is by definition the set of all sigma, these vectors sigma, such that if you take the dot product of sigma with that normal vector, you get 0, because that's just what it is. Everything, all vectors in this subspace here are orthogonal to xi. So you have this definition, and we also know that rho k is even. How do we know that it's even? Because k is origin symmetric. So it's an even function, which shows up important later. And then for the next line, he kind of, my instructor kind of changes variables to what is this, psi? Yeah. Which is okay, but it got, it's kind of confusing because he throws sigma, theta, and psi, and xi all over the place. Too many Greek letters is what I'm saying. So you take this integral, I move it down here, I just rewrote it in a nice way. And what do you know? We know that this is equal to a constant. So I'm skipping this line and going down here. It's equal to a constant because we said it was in the very beginning. This volume is equal to a constant. And one way that you can write this is you can write this constant as the integral of that constant times n minus 1 divided by the measure of this space here. Because if you integrate, if we just pull this stuff out here, what are you going to get here? You're going to get the measure of this space here. And the measure of this space will cancel with this number, n minus 1 will cancel with this, and you're just left over with the constant. And it's a complicated way of writing it, and the question is, why are we writing it this way? And the reason we write it this way is because if you push this inside the integral, and you combine this n minus 1 with this constant, you'll just get a different constant, which we denote as constant tilde. So all of this just to say that this integral is equal to 1 over n minus 1 times integral of a constant. Okay. Next page. If you combine the two integrals by subtracting the left side from the right side, you will get, why is my paper cut? That's bugging me. If you move this integral to the other side and then subtract and combine under a single integral, you'll get this equivalence statement. That this function minus this constant, and if you integrate, you get 0. And that has to be true for every theta that you choose in S. Again, we switch from theta. I think there's a lot of change of variables here, but it all makes sense. I think the notation was a little bit sloppy, but it's fine. And this is where the trick comes from. So I said we needed a lemma or a corollary. We called it a corollary in class. Is that we need to invoke the Funk-Hecke theorem, I think is it's called, which says the following. If you have a function that is continuous on the shell of the sphere, the outside part, such that if the integral of f over this orthogonal subspace is equal to 0, and that's true for every theta, if your function is continuous and it has this integral property, then it is enough to say that f is an odd function. So I don't prove that here, we just used it. We actually covered it in class yesterday. This corollary says that this function is not even, but continuous, definitely, because rho is an even function, raising it to n minus 1 is even, subtracting constant is still even. And we're saying that this integral is equal to 0 for every theta. So that means that this function must be odd. So this function is odd. But rho k is an even function, which means that if you take an even function, raise it to n minus 1, it's still even. And if you subtract constant, still even. So this means that you have this function inside is simultaneously even and odd, which means that the function has to be identically equal to 0. Because that's the only function that I believe is both even and odd. And if it's identically equal to 0, all you have to do is algebra, just move the constant over, take the n minus 1 root, and you'll see that the radial function itself is constant. And if the radial function is constant, then the only possible shape that you get is the ball. So k must be a ball, and that's the end of the proof. It's kind of slick. I thought this theorem would take a lot longer to prove, but you do use this little trick here in the corollary, so that kind of shortens it up. And why did I show this? It's because there is a potential PhD problem. I say that because my instructor asked, it's a famous problem, that if you solve this, then it's for sure worth a PhD. So my ears perked up. I was like, I want a PhD. So here's how it's related. You have a body that's origin symmetric, and it's a convex body. So far, everything's the same. And we say that for any vector, any unit normal vector that we have, we say that the volume, except this time we're looking at n minus 2, of the boundary of k intersected with this guy is constant. And then the question is k a ball? So this is I shouldn't put theorem because we don't know what it is yet, so problem. So all this is saying, how this is different from the previous problem, is that you said the areas of the cross sections were always constant, regardless of how you slice the potato. But now you're just looking at the perimeter of the cross sections, and you're saying those are constant. And this is a lot difficult, or this is much more difficult, because you don't have the radial function trick in this one. There's a convolution that's involved in the previous theorem that's embedded in the corollary that you can't use here. And that's what makes this problem difficult. And then in class he said if you solve it, you essentially, that's worth a PhD to him. I don't know if I'll be able to do anything with this, but it intrigued me enough to where I wanted to look at it more. So most likely won't be able to do anything with it, but that's one of the things you do in a PhD program. You just look at a bunch of problems, hopefully you can make progress on something. Anyway, this video is way too long, so I'm going to call it quits here.